In the previous video, we've seen how we can use the trigonometric ratios to find the length of an edge in a right-angled triangle if we know the length of one of the other edges and we know one of the angles other than the right angle in that triangle. But what if we had the length of two edges and we wish to find one of those angles? Well, we're going to need the inverse trigonometric functions to do that, and those functions are the focus of this video. So let's look at one of our trigonometric ratios. I'm going to pick on our sine ratio, and this tells us that for a given angle theta, the sine of that angle is equal to the opposite edge divided by the hypotenuse. It's telling us that there is a direct relationship between the angle in this triangle and the ratio of these edges. And we've seen that because of the way a triangle is constructed, the ratio of these edges explicitly defines that angle. So there is this explicit connection between the angle and the ratio of these edges. Therefore, if we can convert from an angle into a ratio, we surely must be able to convert back again from a ratio into an angle. Well, we thought about sine as a function previously. We thought about it as being a function where we put in an angle and it generates some value. And we've seen now that that value has a direct correspondence to the ratio of the opposite and hypotenuse. So sine as a function takes in this angle theta as its input and generates the ratio of our opposite and hypotenuse as our output. But there's another concept that goes hand in hand with functions, and that is the idea of an inverse of a function. The inverse of a function does the opposite to its function counterpart. So if a function takes in an input and generates an output as a result, the inverse of a function will take in that output and use it as the input, and it will tell us what input we used in the original function to generate that output. So if we had an inverse function for sine, it would take in our ratio as an input, and it would tell us an angle theta that could have generated that ratio. So what we need is an inverse function of sine to be able to calculate an angle in a right angled triangle. And there is an inverse function of sine. It's known simply as inverse sine. Although there are a couple of different ways that this can be written, both in terms of programming notation and in terms of mathematical notation. So the inverse sine, as most commonly written in programming notation, is written as arcsine, which is spelled A-R-C-S-I-N, arcsine of x. Sometimes that's actually abbreviated to a sine of x. So what does this mean? Well, x is the input to our inverse function. We've said the input to an inverse function must be the output of its function counterpart. So x is our ratio. It's our ratio between the opposite and the hypotenuse. We put that ratio in as the value into the function, and our arcsine function is going to return to us a value for theta that can generate that ratio. So that's the programming notation. It's the way you're most likely going to encounter this if you're dealing with various maths libraries in programming languages. But there's also a mathematical notation, which is the way you're likely to encounter this if you're dealing with more sort of theoretical maths textbooks and the likes, and that's written as sine to the minus 1 of x. This is a special notation that simply means the inverse sine. So all of this means an inverse sine function. X again is our ratio between the opposite and hypotenuse, and again it's going to tell us an angle theta that can generate that ratio. So it's just a special notation that means the inverse sine function. Well, whilst we're talking about special notations, it's actually worth discussing another common notation with the trigonometric functions, such that you don't get confused between this inverse notation and the other common notation, because they are pretty much the same notation. It can get a bit confusing. So this other notation deals with if we have the sine of an angle raised to a power. So for example, if we had the sine of an angle and we decided we're going to take the result of that and we're going to square it, there's a notation that allows us to write this simply as sine squared of theta. This notation, sine to the power of 2 of an angle, means we take the sine of the angle and then we square the result. So it's the same as writing this, sine of theta, and then we take all of that and square it. Of course, this is a pretty much identical notation to where we have the sine to the power of minus 1 of x. This, when it's to the minus 1, is a special notation that means the inverse sine. So although it looks almost identical to when we're raising to a power, in that case alone, it's just mathematical convention. Don't ask me why they've decided to go this route, because personally it is a little confusing because they look like they're both to the power. But in this case and this case alone, when it's sine to the minus 1, it means that it's the inverse sine and not sine raised to a power. So it's really just worth keeping that in mind, that only in this case, this is a special case, and it means the inverse sine function. So we've got our arcsine of x, or our sine to the minus 1 of x, and that's our inverse sine function. And that means, given the ratio between our opposite edge and our hypotenuse, we enter that as the input to that function, and the function is going to tell us an angle theta that generates that ratio. And that seems pretty simple. However, there's actually a little bit more involved with the inverse trigonometric functions than first meets the eye. So up until this point, we've been thinking of our inverse sine function as taking in our x value, which we've said is our ratio, the opposite over the hypotenuse. But earlier, if you recall back, we said that an inverse function takes the results of the function. So really what our inverse function is taking in is some value of sine theta. Rather than thinking of it taking in a ratio, we're actually taking in some value of sine theta. So this allows us to rewrite, if you will, our equation in the following manner. So we're taking into our inverse sine function some value of sine theta, and we're saying that should, so we're questioning, does this give us the original value theta that we put into that sine equation, that sine function? Well, to see this, to understand does it give us this value of theta, we need to think back to our graph of sine theta from an earlier video. So allow me to bring up that graph from an earlier video. So there's our cosine graph, here's our sine graph. But we can see on this graph that for any value of sine theta, for example 0.5, there are actually multiple values of theta that generate that same value of sine theta. And we know this because sine is periodic, so it repeats every 360 degrees, and that means that every 360 degrees there's another value of theta that generates the same value of sine theta. But also we can see that it is demonstrating some symmetrical properties as well. Between 0 and 180 degrees, it's as if we're mirrored about 90 degrees. This part of our curve is a mirror image of this part of our curve. Likewise, between 180 and 360 degrees, it's as if we're mirrored about 270. So this part of the curve is a mirror image of this part. And because of that, even within one 360 degree period, there are two values of theta that can generate the same value of sine theta. So going back to our rephrasing of the equation, if you will, so going back to this question here, as I grab a layer, there we go, we can see that there are many different values of theta that we can input into our sine theta equation that's going to generate the same value of sine theta. Now obviously our inverse sine function, if we give it the same value of sine theta, it needs to generate the same value of theta. We can't just guess which value of theta could possibly generate this from all the different infinitely long list of values of theta that could generate the same value of sine theta. We need to have some consistent result. But the only way we're going to get a consistent result is to restrict the range of our inverse sine function. That is to say, if we look at our graph again, that is to say we force our inverse sine function to return between two specific angles, such that there is only ever one angle of theta that generates a specific value of sine theta. And in the case of our inverse sine function, it's restricted between the range of minus 90 degrees and positive 90 degrees. So it only ever returns an angle theta in this range. In doing this, we get a consistent answer. Every time we input a specific value of sine of theta, so some value between -1 and 1, it's always going to return the exact same value of theta. We can see there's only ever one value of theta for each value of our sine of theta. So we're going to get a consistent value. But what that means is we do need to take careful note of the fact that our inverse sine function for a given value of theta as an input won't necessarily give us the same value of theta as an output, because the sine of some value of sine theta is restricted between the range of -90 degrees is less than or equal to our angle, which is less than or equal to a positive 90 degrees. So theta can range between -90 and 90 degrees. And the clearest way to see how this could be an issue, how we could put a value of theta into our original sine theta, then calculate the inverse sine of that and get a different angle back, is to use an example to actually help visualize this. So I'm going to bring back our graph. Do bear with me jumping back and forth, but hopefully this is really helping to demonstrate things. And I'm going to delete out our earlier workings. Fantastic. So let's say I picked on some random angle. In this case, I'm going to pick on 135 degrees, which is halfway between 90 and 180. So I'm going to pick on 135 degrees. And if I took the sine of 135 degrees, I know that is approximately equal to about 0.707. So the sine of 135 degrees is about 0.707. If I took that value and put it into our inverse sine value function, so if I took the inverse sine of this, we know our inverse sine function only returns between -90 and positive 90. So it's not going to tell us that we had 135 degrees as our angle, because 135 degrees is outside of that range. What it's going to do is it's going to find the angle that is within this range that has the sine of that angle equal to 0.707. And we can see on our graph that that angle is 45 degrees. So the inverse sine is going to tell us that our angle is 45 degrees, but we know in truth that the angle we put in is 135 degrees. And we can see this if we use a scientific calculator. So if I bring up a scientific calculator, we all know now how we can use this to calculate the sine of an angle. So I am in degrees. I'm going to calculate the sine of 135 degrees, just as we did on the whiteboard. We can see that's about 0.707. And now if I was to calculate the inverse sine of this, we're going to see that because we're restricted between that range, it's going to return to us 45 degrees, not 135. So let's see how we can use the inverse functions on this calculator. We've got a button here that's INV. This actually gives us the inverse function. So before, notice we had sine here, and we clicked on sine to calculate the sine of our value. If I click on INV, that toggles us into the inverse mode. I can toggle on and off. And when I'm in the inverse mode, you'll notice sine has now become sine to the -1. That is the inverse sine. So if I now click the inverse sine, it's going to calculate the inverse sine of 0.707. That's going to tell us an angle theta that could generate this value of sine theta. And we said that because there are many different values of theta that can generate this sine theta, for example, 135 degrees can generate this sine theta, we have to restrict the inverse function to a specific range. That range is -90 degrees to positive 90 degrees, and that means that we're going to find, in this case, that 45 degrees is the only angle in that range that can generate this particular value of sine theta. So if I click on inverse sine now, you'll see we do indeed get 45 degrees back. So it is worth being aware of that when we have an angle, we calculate the sine of that angle. If we then put that back through the inverse function, it's not necessarily going to give us the angle that we originally had. Now, lucky for us, when we're dealing with right-angled triangles, and I will stress this is only when we're dealing with right-angled triangles, we know that none of the angles in our triangle are going to be greater than 90 degrees. We know this because our right angle itself is 90 degrees, and we saw in volume 1 that the three interior angles of a triangle, they add up together to 180 degrees. So we know if in total all three angles are 180 degrees and this angle is 90, that means these other two angles must add to 90 degrees. And we know that no angle in a triangle can be 0 degrees or can be negative. That's just not physically possible for an angle in the triangle. It must be greater than 0 degrees. Therefore, if both of these angles must be greater than 0 degrees, none of these angles, if they add to 90, can be 90 degrees or greater. So that means when we're working with right-angled triangles, the angles that we're trying to find are going to be between 0 and 90 degrees, and they're not going to be 0, they're not going to be 90, they're going to be between those values. And that means that those angles are always going to be in this range. We can see that angles between 0 and 90 degrees always fall in this range. So when we're dealing with right-angled triangles, if we have this ratio opposite over hypotenuse and we put that into our inverse sine function, it will give us explicitly the correct angle for our right-angled triangle. Again, we can only make this assumption with right-angled triangles because in a right-angled triangle we know that one of the angles is 90 degrees. Okay, so moving on, we've seen that using an inverse function for sine, we can convert a ratio back into an angle, but in a similar way there's an inverse function for cosine and an inverse function for tangent. Again, these could be written as the arc cosine or arc cos or arc tangent, arc tan of x. Similarly, they can actually be abbreviated to a cos and a tan, and they can be written as cosine to the minus 1 of x and tan to the minus 1 of x. They work in pretty much the exact same way, except for they take in a value of cosine of theta, or they take in a value of tan of theta, and they attempt to tell us the value of theta that generated our input value. Now, of course, again, if we looked at our graphs really quickly, so here is our graph of cosine of theta. Again, we can see it's periodic, and we have some symmetry in the graph, and because of that, we again are going to have to restrict our range. And if we looked at our graph of tan theta, we can see that we are periodic. So again, because of that, there are multiple values of theta that can generate the same value of tan theta, and that means again, to get a consistent result for any value of tan theta put into our inverse tan function, we must restrict the range. So what are those ranges that these two new functions are restricted to? Well, our cosine inverse function, our inverse cosine, is restricted between 0 degrees and 180 degrees. If we take a look at our graph of cosine, we can see that between 0 degrees and 180 degrees, we do indeed, in this range, have only one value of theta for each value of cosine of theta. So by restricting it between 0 and 180, we are indeed guaranteeing that we have this consistent relationship. If we took a look at our tan of theta, that's going to be restricted between negative 90 degrees and 90 degrees. In this case, you'll notice it doesn't actually include negative 90 and 90. It's theta is greater than 90, not greater than or equal to 90, and it's less than or 90, not less than or equal to 90. That's not essential knowledge, but it's worth pointing out, and that's because if we looked at our graph of tan really quickly, we can see, well, by going between negative 90 and positive 90, we only have one period, and that means that we only have a single value of theta for each value of tan theta, which allows us to get that consistent result. But if you recall, at negative 90 and at positive 90, our value of tan theta is equal to infinity. So because of that, we can never actually return negative 90 or 90. We're only ever returning between those values where tan theta is not equal to infinity. Alright, so now that we've seen our inverse trigonometric functions, let's use them to actually find the angles in a right-angled triangle. So I'm going to bring up a new whiteboard to work with. Fantastic. Scroll on up, and I'm going to draw a right-angled triangle, so something like this. Excellent. And then let's make sure we note that this is indeed a right-angled triangle. I'm then going to bring up a layer to draw on. And I'm going to say that we know the hypotenuse of this triangle is 15 units long, that this edge here is 10 units long, and I'm interested in finding this angle in the left corner of the triangle. So the first thing we need to do, much like when we were trying to find the edges in a triangle, is we need to label the edges of the triangle as they relate to the angle we're trying to find. So we know, again, this edge is our hypotenuse, so I'm going to label that H. This edge here is next to or touching our angle, which means this is our adjacent edge, and of course the third edge is opposite our angle, so this is the opposite edge. So now we know that we have the length of our hypotenuse and we have the length of our adjacent edge, and that allows us to calculate the ratio for our cosine, because we know the cosine of our angle is equal to the adjacent over the hypotenuse. That's equal to 10 divided by 15, which is equal to 2/3. So we've got this ratio. We know that the cosine of our angle is equal to 2/3. But now we can take that and we can find our angle theta by using our inverse cosine function. We know that if we had the inverse cosine of 2/3, that is going to tell us that angle theta. We know theta returns between 0 and 180 degrees, thus it must be the correct value for the angle in this triangle. So we can now find the angle of theta using our inverse cosine function. I'm going to do that using a scientific calculator. So if I bring up our calculator and I find our ratio, so 2 divided by 3, so that's 0.66666 recurring. So we've got that, and now I want to find the inverse cosine of that value. So I'm going to click on inverse, click on cosine to the -1, and that's going to tell us that the inverse cosine of 2/3 is about 48.189 degrees, or even 0.190 if we were to truly round this up. So 48.19 degrees. We can also see that we are indeed getting a value in degrees because our calculator was set to degrees. Had we set our calculator to radians and performed the same inverse cosine, it would tell us that the inverse cosine of 2/3 is 0.841. This is the exact same angle, it's just that this angle is using a different measurement. It's measured in radians rather than degrees. I'm going to be working in degrees, but I did want to point out that you can use the inverse functions in both degrees and radians, much like you can use the standard functions in both degrees and radians. So we know that this angle theta, is about 48.19 degrees. Fantastic. So let's now find the other angle in our triangle. Well, we know that the angles in the triangle add to 180, so we could say that this angle, which I guess I could call beta, if this is theta, we could say that beta is equal to 180 degrees minus our right angles 90 degrees minus our 48.19 degrees, and that's actually going to tell us, and this is approximate because we know our 48.19 is approximate, that's actually going to tell us that this is approximately 41.81 degrees. But what I'd like to do is actually use our inverse trigonometric functions to find this angle. So if we're dealing with beta, we know that in relation to beta, the hypotenuse is still the hypotenuse, but this adjacent edge now becomes our opposite edge. So we're dealing with a hypotenuse and opposite. That means we're dealing with the sine of beta is equal to the opposite over the hypotenuse. That again is equal to 10 over 15. We can see again our opposite, which is now this edge, is 10. Our hypotenuse is still 15. So it's equal to 10 over 15, it's equal to 2/3. That means the inverse sine of 2/3 is going to give us beta, which is approximately equal to, if we use our calculator, 2 divided by 3. We are in degrees. I'm going to take the inverse sine of that. It's approximately 41.81 degrees. So 41.81 degrees, which we have seen to be true. And that's all there is to it. Again, if we're trying to find an angle in a triangle, we take the edges that we know, we work out the relationship of those edges to the angle that we're trying to find. We find the trigonometric ratio that defines that relationship. In this case, we're dealing with beta, so we're dealing with sine of beta is equal to the opposite over the hypotenuse. We calculate that ratio using the values that we know, the lengths of the edges. Once we have that ratio, we can calculate the inverse sine, in this case, of that ratio, and that will give us the angle. Once again, just make sure that you are, if you're wanting results in degrees, set to degrees on your calculator and not radians. But that is all there is to using the inverse trigonometric functions to find angles in a right-angled triangle. Alright, so let's put this new knowledge to the test. I'm going to set you a few questions to work through on your own, and just to note, I am going to be working solely in degrees for these questions and not in radians. Starting out with question 1, and let's give myself a new whiteboard to work with. Fantastic. So I'm going to draw a triangle. So here is a right-angled triangle. Excellent. And this is question 1. And this question, we know that the hypotenuse here is 9. This edge is 7 units long, and I'd like you to find the angle that I've just marked with a question mark. So go ahead and pause the video, give this question an attempt. If you have the solution or if you get stuck, unpause the video. I am going to work through the answer on the whiteboard. Okay, welcome back everyone. So what's the first thing we need to do? We need to find out the naming convention of our edges in relation to our angle. And in relation to the angle, well, we know that this edge is our hypotenuse, it's always the hypotenuse, and the other edge that we know is opposite to our angle, which means this is our opposite edge. Once we have the relationship of the edges to the angle, we can decide which trigonometric ratio or which trigonometric function we're going to be using. In this case, we know that the sine of an angle, so sine of theta, is equal to the opposite over the hypotenuse. So it's the sine that relates these two edges that we know. We can calculate that ratio, the opposite over the hypotenuse. It's equal to 7 over 9. Now that we have that ratio, we can use our inverse sine function to calculate our angle. So we can use the inverse sine, and we're going to find the inverse sine of 7 over 9, and that is going to tell us our angle, which we could call theta in this case. So I'm going to use a scientific calculator to get that value. So we take 7 divided by 9, which is 0.777 recurring, and then I'm going to calculate the inverse sine. So I am in degrees. I'm going to click on inverse, click on sine, and that's going to tell us that this angle is approximately 51.058 degrees. So this is approximately equal to 51.058 degrees. So if you got that answer, well done. If you didn't get the answer, make sure again that you're following the steps correctly. So make sure the first thing you need to do is decide on the naming convention of the edges in the triangle. Once you have that, find the trigonometric ratio that relates those edges to the angle. Once you have that, calculate the value for the angle, then use the inverse of that trigonometric function. So in our case, that was inverse sine of that ratio to get the angle. Make sure you are using your scientific calculator correctly for the inverse functions, and make sure that you are set to degrees. You won't get 51.058 if you were set to radians. But hopefully you will manage to follow along and work through that question successfully. So that's question 1. Let's move on to question 2. It's going to be more of the same, if you will. So let me scroll down and draw a new right-angled triangle for us to work with. So I don't know, let's do something like this. This is a right-angled triangle, and I do want to be able to draw on this triangle. So this edge is 12 units long, this edge is 5 units long, and I'd like you to find the angle theta. So go ahead and pause the video, and when we come back I am going to work through the answer on the whiteboard. Okay, welcome back everyone. So the first thing we need to do is work out the naming conventions of our edges in relation to that angle theta. Well, 12 here is our hypotenuse, it's opposite the right angle, so it's always our hypotenuse. And in relationship to theta, our edge that's 5 units long is touching the angle or next to the angle, and that means it is, of course, our adjacent edge. So we need to find the trigonometric ratio that relates the hypotenuse and the adjacent. That would be our cosine ratio. So the cosine of theta is equal to our adjacent edge over the hypotenuse. We can now calculate that ratio. It's equal to 5 over 12. Now that we have that ratio, let's use the inverse of our trigonometric function to find the angle theta. So in this case, because we're dealing with cosine, we need the inverse cosine. So we're going to use the inverse cosine of 5 over 12. That is going to give us the value of theta, and that is approximately equal to, if we use a scientific calculator, 5 divided by 12, and then we want the inverse cosine of that. So it's approximately equal to 65.376 degrees. So the answer you were looking for is around 65.376 degrees. Again, if you got that answer correct, well done. If you didn't, just make sure you're following the steps correctly. Naming convention, once you have that, which trigonometric ratio, once you have that, find the ratio, once you have that, use the inverse of the function in that ratio to actually calculate the value of theta. So that's question 2. Let's move on to question 3. So question 3, and again, let's draw a new triangle for this. So something, I don't know, something like this time. And in this case, this angle here is going to be our right angle. And this edge is 4 units, this edge is 6 units, and I'd like you to find this angle, which I'm going to call theta. So go ahead and pause the video. When you come back, we're going to work through the answer on the whiteboard. Okay, welcome back everyone. So again, we need to find our naming convention. If this is our angle, it means our edge that's 6 units long is opposite the angle, so this is our opposite. And this edge that's 4 units long is touching our angle. And you'll notice because the edge down here is our hypotenuse, that means this, of course, must be our adjacent edge. So we're dealing with our adjacent and our opposite, which trigonometric function, which trigonometric ratio relates the adjacent and the opposite. That's going to be our tangent. So tan of our angle is equal to the opposite over the adjacent. That is equal to 6 over 4. Which is equal to 3 over 2. So now that we have that, we can use our inverse of tan to find theta. So I'm going to use the tan, inverse of tan of 3 over 2. That's going to tell us our angle theta. We can use a scientific calculator to get that angle. So I'm going to take 3 divided by 2, that's 1.5. And then I'm going to calculate the inverse tan of 1.5. And it tells us that our angle is approximately equal to 56.310 degrees. So theta is approximately equal to 56.310 degrees. Okay, so we've had a question that used sine, a question that used cosine, and a question that used tangent. I now want to just set one last question that's going to require combining some of the knowledge from the previous video with some of the knowledge of this video. So I'm going to set a new question. I am going to use a new whiteboard just in case we don't have enough room left on our current whiteboard for all of the workings that we need to do. So this is question 4. And allow me to draw a triangle. So here is a right angle triangle. And I'm going to say in this triangle that this edge is 11 units long and this edge is 8 units long. What I'd like you to do is to use trigonometry to find the length of our third edge. Now again, you could use Pythagoras here, but I don't want you to use Pythagoras in this case. This is just a question to get you using trigonometry as opposed to being an actual practical example of where you would use trigonometry, because you could use Pythagoras to solve this, but I don't want you to use Pythagoras in this case. Please use trigonometry and use it to find the length of that missing edge in the triangle. So go ahead, pause the video, give this an attempt. If you come up with a solution or you get stuck, unpause the video and I will work through the answer here on the whiteboard. Okay, welcome back everyone. So to calculate the length of that third edge using trigonometry, we're going to need to know one of the angles, one of these two angles in our triangle, because we need an angle and an edge to find a missing edge, and currently we don't have an angle, we just have two edges. However, if we have two edges, we can find an angle. We've seen that in this video. So the first thing I'd like to do is use the two edges we know to find one of the missing angles. Then we're going to use one of the edges and that angle to find our missing edge. Obviously, there are quite a few different ways to get the same result depending on which angle you find and then which trigonometric function you decide to use to find the edge. I'm going to tackle this in one way, but you may have used a different approach. As long as you get the same result or very near the same result, giving sort of a little bit of flexibility for rounding errors and the likes, as long as you get near the same result, then that's perfectly okay. So what I'm going to do, I'm actually going to find this angle in the bottom right, which I'm going to call theta. And I want to find theta using these two edges that we know. So this is using concepts that we've covered in this video on the inverse trigonometric functions. So relating to our angle theta, the edge that we don't know is our opposite edge. This, of course, is our hypotenuse. And this edge here is touching angle theta, it's next to theta, it is our adjacent. So we know the hypotenuse and the adjacent, that means we're going to use the cosine, because the cosine of our angle theta is equal to the adjacent over the hypotenuse, that's equal to 8 over 11. Therefore, the inverse cosine of 8 over 11 is going to give us that angle theta. So I'm going to use a calculator to find the inverse cosine of 8 over 11. So I'm going to take 8, I'm going to divide it by 11, and then going to find the inverse cosine. So click on inverse, click on cosine to the minus 1, the inverse cosine. That's going to give us an angle that is approximately equal to 43.342 degrees. So theta is approximately 43.342 degrees. Now that we know that angle, we can use this angle to find our opposite edge, because we can relate the opposite edge and our angle and one of the other two edges using the trigonometric ratios, and in doing that we can find that missing edge. Now in this case I'm going to use the hypotenuse in the opposite edge, and that means I'm going to use the sine of our angle. So we know the sine of theta is equal to our opposite edge divided by the hypotenuse. That means our opposite edge is equal to the sine of theta multiplied by the hypotenuse, which is equal to the sine of 43.342 degrees, or I should say approximately equal to, since this is an approximate value, multiplied by 11. So if we use a calculator to work that out, I am in degrees, so 43.342 degrees. The sine of that is 0.68 or so. And I'm going to multiply that by 11. And that tells us the length of our edge near enough is 7.550 units. So that's approximately equal to 7.550. So the length of our missing edge is 7.55. If you got a value around that, that is the correct answer. Now if we wanted, we could actually check this using Pythagoras' theorem. I said not to answer the question using Pythagoras' theorem, but there was nothing preventing you from using Pythagoras, just to check to make sure you'd got the correct answer. So we know if our opposite edge is 7.55 units, that the opposite edge squared plus our adjacent edge squared must be equal to our hypotenuse squared. That means 7.55 squared plus 8 squared should equal 11 squared. Well, 7.55 squared plus 8 squared is equal to, as we use a calculator, so 7.55 times 7.55, that's equal to 57, plus, well, 8 squared is 64, so plus 64, so that's equal to around 121. So that's equal to approximately 121, given our rounding errors. Well, the other edge, our hypotenuse, is 11. So 11 squared is equal to, now I know the value of this, but I will use a calculator just to prove to you that I'm not cheating here. 11 times 11 is equal to 121. So we can see that indeed our value of 7.55 is close enough to the actual length of this opposite edge. Fantastic. And that really is all there is to using the inverse trigonometric ratios to find the angles of a right-angled triangle if you know the lengths of two edges. So again, the only tricky part here is to make sure that you remember that those inverse trigonometric functions return values within a certain range. Now again, it doesn't affect us when we're dealing with right-angled triangles, as we explained earlier, but if you do start working with other triangles and using trigonometry and those triangles aren't right-angled, you really do need to be aware of how the range of these angles can affect us. And this is something we are going to see in later videos. But hopefully you can already see the true power of our trigonometric functions, our trigonometric ratios, and the inverse trigonometric functions that we took a look at in this video for solving problems that relate to triangles. So in the next video, we're actually going to apply these functions to solve a problem to further illustrate how useful they can be. So thank you for watching, and I hope you join me in the next video.